so our next talk is going to be by Amanda Cook, and it'll be Spectral and Imaging System for Identifying Hydration on Airless Bottles.
Okay, thank you. So as the title says, I'll be talking about an instrument that will be able to detect volatiles on the surface. But before I go on, I just wanted to acknowledge this awesome team of people. Tony Colaprete is the PI of this instrument in its many forms. And then we've got Ted Rausch, who's here at this conference, and then a slew of engineers, Josh Benton, Josh Forgione, Rich Bilowski, and Bob McMurray, and Aaron Fritzler is our instrument manager. And this is more than a team to me at this point. This is kind of our work family. So proud to work with those people. So this is the instrument I'm going to talk to you about today. It's called NIRVSS. It's what it is. And that stands for Near Infrared Volatile Spectrometer System. Tony was hoping it'd be pronounced NIRVSS, so maybe we can get that to catch on. But it's basically consists of these two parts here. This is a dual spectrometer. Near infrared spectrometer spans 1600 to 3400 nanometers. It's got optical fibers that connect into the second component, which we call the bracket assembly. And so these fibers, for those spectrometers, the light source here is an infrared lamp. And you'll see that this entire bracket assembly is kind of angled down. It's meant to, on the Resource Prospector rover, be mounted on the belly of the rover, looking down at the ground as the rover moves along and as it drills. So the rest of this instrument, there's a CMOS high-resolution camera here. Comes with 8 color LEDs ranging from 410 nanometers to 1050 nanometers. And then we've also got a set of 4 radiometers to calibrate surface temperatures for the spectral measurements. So with this spectrometer, this is the wavelength range of NIRVSS, about 1.6 microns to 3.4 microns. We're primarily interested in water, of course, and these are the 2 bands that are most indicative of water in our wavelength range. This 2 micron band here, and then this huge 3 micron band. This 3 micron band is particularly sensitive to very low concentrations of water, down to 0.5% or even less. So what we typically do is we look at these bands in real time. We're taking spectra faster than every second, and we measure these band depths in real time as we're roving along. And so this is exactly how it works, or will work, for the Resource Prospector mission. You've seen this cool glamour shot of the rover, and NIRVSS is kind of hanging down here at the belly of the rover. And so the way this works, again, is we're taking spectra as we're roving along, measuring band depths, those water band depths as we go. And in real time, we'll be able to plot out those band depths on the map of the lunar surface and kind of create these heat maps that tell us where the highest concentrations of water right now, where the highest concentrations of water are. So in this map, here's a higher concentration of water that we detected in a simulation, a planetary analog, and it's actually not water, as Rick Elphick likes to point out. It's a piece of paper, isn't it, or plastic? So it's a lot of OH there. But this is how it would work for a Resource Prospector. We would, using the neutron spectrometer and the NIRVSS system, make maps like these to determine where the coolest spot is to drill. So obviously it's here. So then we park over this spot. And again, I didn't mention this, but we do this horizontal characterization of water deposits, but we also do a vertical characterization of those deposits. So here's a drill cartoon, and the drill goes into the surface. It delivers cuttings to the surface in the NIRVSS field of view, and we measure the water content of those cuttings as they're delivered to the surface. So we get a distribution of the volatiles with depth. So just a little bit more detail on how that drilling process works. This is a honeybee drill made by Chris Zachney's company that was just before me. This is the honeybee drill, and what you're seeing here is a soil tube filled with lunar simulant. It's in the dirty vacuum chamber at Glenn Research Center, and Again, it's filled with very cold lunar simulant, and we're running our drill test here. The drill is actually going into the surface here, and as it's retracted, it's passively brushed by this brush here, and so the soil is brushed off of the flutes, and then it passes through this chute down onto the surface, and our spectrometer field of view is right about here. So we're watching in real time as these cuttings are delivered to the surface, and this box that this field of view is actually the camera that's on the bracket. So we have this image to give context to the spectral scene. So I would like to play this video. This one here is a video. So you can see the sort of things that we can catch if we watch, and you can see the pile settling. You're going to see a bite get dumped here. You see it's dark material, and then if you pay close attention, you might be able to see that material lighten up as the surface is desiccating in the vacuum chamber. And so you catch all sorts of, a stream of grains flowing down here during this drill test. And so if we had been taking spectra only of this pile, we would see all sorts of weird things happening in the spectra. Wouldn't understand exactly why all of a sudden did it look like there's some water when we weren't even necessarily delivering stuff to the surface at that point. Well, the pile collapsed. So having these context images is really important for interpreting our spectra. Okay, so here's another video, and you can go ahead and play this one too, if you don't mind, that kind of separates out the bites. So there's the first bite delivered to the surface, bite number 2. Bite number 3, and you can kind of see, catch the wheel, the brush spinning. Bite number 4. We got 5, but then 6 and 7 kind of muddied. So what happens is the chute here gets clogged, and we know that can tend to happen, which is why I asked Chris that question. And so, we tried, how about having an overflow chute for when the chute clogs? Well, it turns out it didn't quite work as well as we thought for this test, so the drill team is redesigned to help us see all of the material from each depth. So, and this is why you do tests. So, in addition to getting the in addition to getting the spectroscopic information, we get all this imagery, and now that we have these multicolor LEDs, we've got an opportunity to try to do some science, including volatile detection using just the camera. And so we started with some very basic camera data analysis. What I'm doing here is I'm using the drill itself as a reference, and I'm averaging, the brightness of the pixels in that area, and then I do the same for the pile, and I do this for each LED wavelength. And then, of course, I get the relative brightness by dividing them. So here's an example of how that works out. What's plotted here are the brightnesses as measured with 3 different LEDs as the illumination source. In blue, that's a 740 nanometer LED. You can see there's not a lot of exciting changes going on at that wavelength. It's because there's not a lot of water bands at 740 nanometers. But if you look at 940 and 1050 nanometers, where there are some water bands nearby, particularly the 1050 is right near kind of a broad water absorption, you can see that there are these dips in brightness at the surface. And without comparing this to any other data, my first inclination is, these are the bytes being delivered to the surface. So what we can do is then compare this data to the spectral data. So here's this slide is going to take a second to go through, so relax, I'm going to walk you through it. On the x-axis here is time. On the y-axis over here is the 3-micron band depth. That's plotted in black. So just focus on the black for now. What's going on here is the soil is being delivered to the surface. The 3-micron brightness jumps and then slowly declines as the surface is desiccating. And the same thing happens over and over again as fresh material is revealed at the surface. What's plotted in purple here is the drill depth. So you can see that this drill depth right around, so remember we do this in 10 centimeter bites. So we've already been to 40 centimeters at this point, and so we started drilling new material here down to 50 centimeters. And that's when new material gets delivered to the surface. At this point, you notice that, here the peak of the band depth corresponds to the lowest depth of the drill, and here it doesn't. This is a pile collapsing. So we see that the 3-micron band depth shoots up a little earlier than we expect, and it's because the pile collapses. It reveals the wet material that's kind of been hidden underneath, and so you get an early jump. But then you also get this normal, this timing that we actually expect when material actually comes out of the chute. And same for this point. So if you compare this to some of the camera data, you can see that it follows a similar pattern. These are more or less aligned with the drilling depths. There are some misalignments that I can't quite line up the drill with the image data. So we're still kind of working on this interpretation. This drilling sequence and how the mechanics of all of this works is much more complicated than we expected. So we're still working on the interpretation. But the good news is you can get something like spectral information from these LEDs and the camera. So on that note, then we can take a look at some different kinds of rock samples here with our camera and measure them at all of the 7 wavelengths we have with our LED bank. And we can get some very crude or coarse spectra of rock samples in the same way. Again, and this is the last little bit here. I wanted to mention that this instrument has multiple uses. It can be used on a rover, it can be used on a lander. It can also be carried by an astronaut, which is a new thing that we're working on with the Basalt team and the Finesse team. And so the idea is that we fit the entire instrument and all the electronic support equipment into a large backpack and carry it around like total cool people with awesome jobs and take measurements and pretend to be astronauts and get paid to do it. So this is a really cool new project where we're trying to, Jen Heldman, who leads the Finesse project, and Darlene Lim, who does Basalt, we're trying to modify these instruments for use with astronauts. And so this is the version of our instrument that we're building right now. And this piece will supposedly fit in a backpack that I can carry. And so this is the bracket, and it's pointing directly down this time. You got the fibers onto the spectrometer, which is hidden in the back here. Should be less than 35 pounds. Spectrometer fields of view can be reduced by some lenses that we are adding to the bracket, so that we can, instead of investigating a very large field of view, we can look at very small features in the rocks, potentially for volatiles or also for life detection. So of course, I don't need to repeat this to this audience, but volatiles have been detected on many airless bodies. This instrument is relevant to use on many of those bodies. So here's a summary. I'll let you read that, and we can get to questions if you have any.
We have time for questions. Well, Carly gets the mic. I have a quick one. I noticed that. Well, we'll let Carly go first.
Oh, go ahead.
I was curious how robust your mechanism is to different substances. Like, I was thinking about in Colorado we have a lot of clay, and how much do you have to worry about clogs and things?
Oh, you moved the drill. Yeah. So this might be a better question for Zach, but the drill, it does. You mean the chute itself? Yeah. How robust is it to clogging?
Yeah, you have to worry about that because I can imagine
yes.
clays could be present on.
Yeah, we definitely have to worry about it, and the test shows it. Unfortunately, the simulant that we use in this test isn't necessarily representative of the stuff that we predict we'll be encountering at the poles. It's more like the really, really jagged stuff that Chris Sackney was talking about. So yeah, it is something that we have to consider, and it's actually something that we kind of, to some extent, just have to accept and try to mitigate. So we've worked with the drill team to try to build kind of an overflow chute that still drops stuff into our field of view when the chute does get clogged.
Okay, most of my questions are more technical, and you probably said them, and it went so quickly I didn't catch them. First question is, what's your light source for the spectrometer?
Yes, the light source is it's a tungsten filament.
So you're bringing your light and you're
That's right.
shining it on the area. Okay, and then the field of view of the spectrometer is looking at the bulk area, I presume.
And that's right. It takes up
Okay.
about, of those videos that you were seeing, it takes up
Okay.
about a third of that field of view. The spectrometers can look at that area.
Okay, then but the data you showed us was a time variation.
That's right.
So
Yeah.
you're obtaining a time series of spectra.
Yes.
For each of the spectrum, then, do you have is it a linear array that you obtain it simultaneously, or do you obtain it from one end of the spectrum to the other as a function of time?
I'm not sure I'm quite getting your question, but I think maybe you want to repeat?
Okay, let me repeat it. Are
You
you
have to
obtain?
quickly repeat.
Okay, are all wavelengths obtained simultaneously?
Yes.
Okay,
Yes.
got that.
That's correct.
And we are going to have a discussion period
Okay.
after
I
this
can
next
catch you later.
talk, so we can even come back to this if you like. So, okay, thank you.